start. Okay, thing. Okay, fine. Okay, it's happening. So okay, so most of you are answering it as a B. The correct answer is B. The lowest point with a specific region is called to be the. So here I asked about the local minimum. So it should be the specific region lowest point, not throughout the entire solution. What is the minimum point of this function? So this is a function given to you, and what is the minimum point of the function? So whenever someone asks you minimum point, maximum point, stationary point, or stationary point, so you have to calculate derivative and then derivative make it is equals to 0 and then calculate the value of x for that. So this is the function. So first calculate derivative. Once that is done, make it is equals to 0 and then calculate the x values for that. Okay, 1a. So yeah, Ravi and Srihari, you are correct. So x is equals to 2 and f of x is equals to 1. So one who are not able to solve it, so let's deep dive. To find the minimum point, we take a derivative of f and set it equals to 0. That's what we first did. So I calculated here derivative of f of x. Derivative of f of x is simple, 2x minus 4, and I make it is equals to 0. So if you make it is equals to 0, I will shift minus 4 here, it becomes plus 4, and then x becomes is equals to 4. It's a very simple. Now put x is equals to 2 in an equation. Okay. Now I put it this in the equation. So if you just put it in the equation, you are able to calculate that 0. So here there are two options which give me x is equals to 2 and f of x if you put is equals to giving you the minus is equals to 1. So that's the minimum point of the function. Moving towards another example. So this is not asking you the exercises, but such kind of might they ask in the paper. So this is kind of they will give some word problem. So with this particular problem, they are going to test whether you understand this concept or not. And this is also I am taking because in your day-to-day life, this kind of a problems might occur. How to use optimization concept and solve those problems. So this is the particular problem of all the rectangles of area 100 which have the smallest perimeter. So right now I am drawing some rectangle. The rectangle who I think everyone knows which having the length opposite side are equal. Okay, are called to be the and having the all angles are 90 degree are called to be the rectangle. Okay, so this rectangle looks like this. So you can the area of rectangle is 100 and which have the smallest perimeter. Okay, so you can have the area 100. You can draw different such kind of rectangles which having the area is equal to 100. So formula of area is equal to length into breadth. Okay, so if you take the length is equal to 20 and your breadth is equal to 5, so 20 multiplied by 5 is equals to 100. You can draw another rectangle which has the area is equals to 100, such as 25 multiplied by 4. So it's just a factors you are taking. 25 is your length and your breadth is 4. So that way I gave the example of two combination. So there are multiple combination, but what is asked? Which have the smallest perimeter? And right now, one who don't know what exactly perimeter. Perimeter it means the sum of distances, sum of all sides is called to be the perimeter. So let's L I take as a length and B is the breadth. To make it more simple, area is equals to length into breadth and the perimeter is equal to 2 times of length because lengths are equal in the rectangle and 2 times of breadth. So breadths are also equal. So 2L plus 2B is exactly the perimeter. Now, now give attention here. So here the optimization function is perimeter. So we want to find a minimum. Smallest means the minimum. So we want to find a minimum perimeter. So what I will do, I will write this particular formula 2L plus 2B. So I brought 2L plus 2B and here my decision variable I'm making it into the L. Okay. Right now I have breadth also in this function. So with the help of this area, okay, I know I want the area, my area is 600. So I convert this whole thing, I convert this B into some area format because I know the value of area. So what I just did, so I know this is 100. So 100 by L, that's what I made here and I put B here. So it's equals to 2 into a by L. So function of L. Yes, correct, Ravi. So I converted this, I transformed this whole problem into the function of L format. Okay. You can also convert some might have the question why I can't convert into the bread. Yeah, you can convert it into the bread format. So it's dependent upon you which decision variable you want to make. So now my whole this function is converted into the L form. Again, I have the function, I have the decision variable. So what I will do, applying first order necessary condition, I will calculate derivative and make it is equals to 0. That's what I did here, and I calculated this derivative and make it is equal to 0. From this, only one unknown is here, that is L, and with the help of L I am able to calculate. So this is the again quadratic problem, so you will have the two solution, so plus 10 and minus 10. Right now someone have the question that L is the length and length can't be negative, so that's why this negative we will cancel out from here itself. Then you will only end up with plus 10. Put this plus 10 here and you know the area is equals to 100, so you will get the breadth also. So you have the length and breadth, you will calculate it, that is equals to 10 length and 10 breadth. And then if you put into the perimeter, so then 10 and 10 if you put, you will get a value 40. So 40 perimeter will, there is a rectangle which having the length is equals to 10 and breadth is equal to 10, which will have the 40 perimeter, which will have the area is equals to 100. That way we solve, and as well as the smallest perimeter. So that way we solve this problem by utilizing the optimization concept. So here also this is kind of a proof of one of the properties, that the rectangle which having the equal sides, which is kind of a square, have the least perimeter. Okay, so that is kind of a proof of particular concept or the particular property which we did here. Okay, another problem we will see, okay, to understand it more better in the real life. So there is some manufacturer determine that the daily average production of q. So let's assume you are building some kind of a product. So you are building a kind of a robot which cleans the day to day, which cleans your house, that kind of a robot. You have the company, and to build that he has particular q. Okay, q value, which is a number of products he is building on day to day basis, and this is kind of a function for which he is calculating the cost. So these are the q number of robots you are making, and c is the cost associated with that. If you make this many products, so this will be the cost of the production. Determining the number of units produced per day, which minimizes your average cost. So here his aim, if you produce so the problem here of this particular is, if you produce in industry, it's like if you produce thousands of product, okay, in a one day, it does not mean, is it does not guarantee that you are going to get a profit for that all the thousand products. Means maximum production, it does not means the maximum profit. Okay, because you have to sell those products in the market as well. Otherwise, if you created or generated manufactured so many products, and if it's on the shelf of your particular what you can say particular shop shelf, it is no one is purchasing that product, and you are just manufacturing that product, that will also reduce your, what you can say, profitability. It's similar like a sweet shop. If you, it does not mean if you produce so many sweets, that sweets also should be sellable. Okay, otherwise it got deteriorated and you will end up as kind of you will end up as loss. Okay, so that's why this is kind of a function, how many units I should make so that I will end up as profit. So this is the profitability function. So here, this is the function given to us. We will first calculate derivative. I calculated derivative. Okay, so right now don't take tension how to calculate derivative and all. So just something is I have done, that calculated the derivative, and this is answer you got out of it. Now I made is equals to 0. So when I make it is equal to 0, so I got a critical solution for this q is equals to 500. So we discussed how to calculate on our previous slide. So I'm right now I'm going in depth. So you get 500 as a q value. Okay. So I will again check different condition, that is checking the second order necessity condition whether whatever the double derivative it is a positive or a negative value. So here again I calculated the derivative and putting critical value in this particular equation. I mean I am getting a positive value through this particular, so by solving this at particular you can say 60. So this is the particular point I am getting the positive value of double derivative, and that's why this is a particular minimum point, and this is at particular q is equal to 500 I'm getting the minimum point. So you are able to see this is kind of a just for the illustrative function. So this is the q curve, and this is you can see q at this particular point I am getting 60. That is the cost of my particular production is 60. Otherwise if I produce my what you can say, if I manufacture lesser than this, then also my cost of production will increase. If I build the manufacture more number of products, again my cost will increase. So with the help of mathematics, and if you know the function, you are able to calculate the minimum value that will take which will that will be calculated with the help of double derivative. You at least know this point. So from this he can take the decision in each day I just will produce 500, and that will give me the maximum profit, not more than that nor less than that. Okay, that's how the optimization problem has been solved. So right now I will give you the example, different example of optimization. Most of you know the Zomato delivery guys and Swiggy delivery guys. So how they have to go from one place to another place. So based upon distance they will calculate, based upon time they will calculate it. So like that, that is one of the example of optimization. Then this is another example in the manufacturing. You can use optimization. Again, you on the daily day-to-day basis, you are optimizing your schedule also. So this is the task I have to do first, this is the task I have to do second. Also you can optimize your whole means if you are the manager, you can optimize your whole schedule accordingly by planning it on the Google Calendar or dividing the task accordingly. So these are different optimization example. So moving towards next, again these are kind of a MCQ. So the first question is, a rectangle has fixed perimeter. I just twisted here the question. Initially we have fixed area. Here I fixed the perimeter. What dimension would maximize its area? So just flipping of the question. So here your function becomes your objective function is area minimum. So you want to maximize area. So I just switch to maximize area. So that is your function, and perimeter is given, that is 221. So for that just go through it. Let's take 1 minute and then you can answer this. So your objective function will be area is equals to length and breadth. Then take L as your function, put B values here. So same question but just asked in a different way. So hope those who understand it, I think you are able to solve. Even if you are not able to solve, we will go through the explanation part of it. So Suchitra answer it as a. Even if you don't know optimization, if you know the properties of maths, I think that way also you can solve it. So Suchita, you answered as A. Okay. So let's wait for the others also. Uh, okay, Abhinav also answered as a B. So you both are correct. So this is one of the property itself in itself. So but with the optimization thing, how we solve? Here I take 2 length multiplied by 2 breadth. It's perimeter format 24. Step 1. So I converted this into the length format. So this is becomes 12 minus b. Here I solved. Okay, you can take a snapshot. Okay, then forming optimization function. Say f of x is equal to area. So I converted into the length into breadth, and then I converted here in the breadth form. Okay, I'm just giving here a kind of a another way to solve the problem. So initially in previous I took the length, here I am taking the breadth here. So it becomes 12b minus b square. So I calculated a double derivative is equal to 0. So this is double derivative 12 minus 2b, and it is giving me b is equal to 6 and l is equals to 6. Okay, so it is giving me the answer b is equal to 6, and that's why I just put it in this particular formula. Then it becomes 6 plus 6 is equal to 6 minus 6 it becomes 0. So that way I solve this. So you will get the answer for this. Okay. Um, so that's what length and breadth is equal to 6. Moving towards next question. Consider this is a function. What are critical values? I already told you what exactly critical value means, at which you are getting the maximum and minimum value. So take your time. Okay, Abhinav answer it as A. Okay. So very simple problem. 2 derivative means 2x square minus again 2 multiplied by 6 Suchita. So yeah, okay. So this is what I answer getting here is equals to d. So let's take it again. So to find the derivative, so this is the derivative 3x square, that is right, minus 12x, that is also right, plus 9, that is also right. When I make it is equals to 0, if I solve this quadratic problem, uh, mm, so um, so if you solve this quadratic problem, I don't know whether, according to you, if you got this particular answers or not. Let's take 1 and 3. Okay. If you take 3 here, it becomes 3, 3 the 9, 27 minus. Uh, so go through this, just calculate the what you can say x value for this particular equation, and I think Suchita and Abhinav, whether I don't know whether I am also correct or not. So if you solve this, if we get this particular 1 and 3 option, then this is the correct option. Uh, if you got this one, just check by solving this particular equation, you are able to get this answer or not. Okay. So I think Ravi, you got also same answer, right? So I think this is the correct answer what I solved. If you solve this quadratic equation, you will get these answers. Okay, that's simple. Okay, then moving towards the next question. A company wants to maximize its profit. So this is the profit function where X is quantity of products sold. What is the optimal quantity of product to sell? So again, you can solve this problem which we just saw. We just saw the one of the examples here. Okay, Ravi answered as B. Okay, let's wait for the other. Uh, so just first calculate a derivative and make it is equals to 0. So you want to just know the quantity of product, right? So here if you want to know the quantity of product, that means you just want to calculate the x value for that. So the correct answer here is the B answer. Sahitya Devi, it's not D. So why it's not D? So just I calculated the derivative here. So derivative it's minus 4x plus 40. So if 40 goes here, it becomes minus 40, and then again it will come here 4. So 40 divided by 4. So x is equals to 10 value. Okay, and that's why your correct answer is 10. Okay, it's that easy. Next one, a car travels along this is kind of a, if you know the bit physics, so this is a big kind of a physics problem. A car travel along a straight road, its position is given. This is your position. So at what position currently I am. So this is the function for the what is the car's velocity at t is equal to 2 seconds. Very simple problem. So just understand the formula of, here I am asking velocity. Velocity just it's kind of a speed only. So I think most of you got the answer. So it's 11. It's D. Those who are not able to solve, why? Okay. Those who are not able to solve, let's understand what exactly velocity. The definition of velocity means distance upon time. Is that simple? So here S means distance is given and time is also given. So you are going to calculate a derivative. So velocity is nothing but a derivative of your distance. So distance function is given. I will calculate a derivative. So it becomes velocity function 4t plus 3, and then I just compare it is equals to so what is the car's velocity at t is equals to 2. So I just put velocity function is given, I put 2 value in this, and 2 multiplied by 4 it becomes 8 plus 3 is equals to 11, and that's how the answer is calculated. So they might give such kind of examples also. So you should know a kind of a background something is related derivative or something, we whatever the terminology they will ask. Okay. So hope you understand the optimization and all, I think, with those examples. With a univariate case. Now we will move towards a multivariate optimization. Here multi means many variables associated in your function. Right now we saw just time or the distance and all those examples. Here we are going to see a multivariate version of it. When there are multiple variation. When you want to minimize your, again we will go and remember that particular distance calculation in the Google Maps. So in that case, if you want a particular path which will give you a less distance as well as less amount of time, this both constraint, this both objective, so in this case your time and your distance becomes your decision variable initially. Okay, so this is how it looks like. Z is a function of x1 x2 till xn. Okay. So for the illustration purpose, we again take the professor's example. Here the function, here you can say it generally they represent this function. So it's a root of x1 square plus x2 square. So x1 is one of the variable and x2 is another variable. So when you draw this function on a particular visualize on a 3D plot, this looks like this. So x1 is this x-axis, and this is your y-axis where all x2 values. So if you put x1 and x2 values, so you will get some y value. So all those y value are given over here. So for this particular x, if you consider this particular x and x1 value, this particular, and this is the y, x2 value for this particular pair. So for this particular, we are going to know what exactly value. Some value will come and we will plot this value or take that value on the z-axis. So if you take all such solutions, you will get one kind of a plot, and that beautiful designs looks like a cone here. Okay, and this green to red portion showing the f of x function. So this means very high values, and this blue portion means this is kind of a heat map they generally call. Now there is another way to visualize this particular thing, that is called to the contour plot, which was shown over here. So let's assume you are going to cut this at particular this. Hello. Okay. So if you are cutting this particular hole, these things at particular distance, cut this, cut this. So like cutting a cake, you are cutting this particular cake cone in a particular distance. So you will get particular same values throughout. Okay. So let's visualize this from the top side. If you consider, if you are, let's visualize you are in this particular 3D space. You are going to visualize this from the top. So if you visualize this from the top, you will get like this. Okay, so at this particular, this will come at this center, and if you go again, some value will come. So if you go far from this particular point 0 0, you are getting your f of x value. You can see here this value is increasing. So if you draw a particular cut here, so you will get all those values. So this is x1 and x2, and these are all the values. If you are getting k, this is kind of a k if you consider a specific distance. So if you take first cut here, second cut here, third cut here, so you will get this kind of a values, contours. So these are called to be the contours. Okay, from the top, and just visualize this particular thing from the top. Hope you understand this. Those who not understand it, just text it again, I will explain. So if you go far away, so this particular point is called to be the minimum point. Here you are able to see. We will understand this more detail in with the taking. So here this is very simple function, and you are having only one minimum here. Okay, take this example. So this kind of example will appear in the when you solve the real life cases. Okay, so this is the function, and this is very complex function, we will not go into that, which having the two values x1 and x2. If you have x1 and x2, so this is very complex, you are able to see, and this red portion showing the highest value of f of x, and the blue portion showing the less value of f of x. Okay, and when you saw in the contour form of it, so this is beautiful pattern will come when you see this from the top. So here this is the minimum point, these are the minimum points, and suddenly some maximum points are, these are local minimums are maximums are coming, these are local minimums are coming. So global minimum is occurring for this particular function at 0 0, but for other function it might occur at anything. So that's what exactly the case. So we will go and see the multivariate version of solving the optimization problem. Again, this is the way. Here you are able to see this is your function. Here as we have multiple variables, okay, Um, okay, will we use partial derivative? That's what we are going to see. That's what I'm explaining, Ravi. So here we have the function. So we are what we will take. We will take a partial derivative. So this is derivative. So those who don't know partial derivative means derivative. If you have multiple variables within your function x1, x2, then calculating derivative with respect to particular variable is called to be the partial derivative. So that's what I am doing, Ravi, here. I am calculating the derivative with respect to x1, that is the partial derivative for a variable x1. Similarly, how many number of variables I will do that. I will calculate a derivative for all those variables. So right now I'm having n variables, so I'm calculating derivative for all those n variables, and that I will stack all those in a particular matrix. So that matrix is called to be the gradients. So in singular case, we call it as a derivative. In multiple case, multivariate case, we call it as a gradient because it's a stack of all those gradients, all those derivatives. So this is gradients is represented with this particular inverted triangle. Okay. So in multivariate case, it becomes a gradient of particular derivative. Now here again we will compare this with the help of zero, and we will solve all those systematic. So right now we saw the linear algebra and we solve the different system of linear equation. So this is that case only. This is the particular function and each function has something, and these are the answers for that. Okay, so this is the correct place we are utilizing our linear algebra concept. Okay, so someone who like why we are studying linear algebra, because of this we are studying linear algebra. Hope you cleared out here. Now this is the kind of a place. Yes, Ravi, it is a vector of all partial derivative. You are correct. Gradient means. Now this is the case where we will get the stationary point, but the case we want to know whether it's a positive, negative, or something like that. So for that there is a Hessian matrix. So Hessian matrix again, how it is look like, it's a double derivative of particular function x1, then you will, so just assume this is your feature 1, feature 2, or till feature n. Okay, and then you will calculate a derivative with respect to feature 1 two times. If it's feature 1, so the first in your mind just take this particular matrix, feature 1, feature 2 till feature n. These are your columns, and then again take a rows, feature 1 till feature n. And if this is particular first feature in rows and first feature in column, so calculate a derivative of f with respect to x1. So at this particular point on x1 is coming and here also x1 is coming, that's why this derivative is like that. But in this case, this is your first column and second row, so it becomes derivative of with respect to x2 and derivative with respect to x1. So this is a kind of your matrix. Okay, feature means columns. Okay, and rows means your samples. So like that you can consider. So this is kind of a Hessian matrix. Just take a snapshot of it and just look properly, you will understand what exactly I mean. Okay, where it is. Okay, okay, so here we are. So this is what exactly Hessian matrix. And once you calculate Hessian matrix, then you have to calculate whether this matrix is positive definite matrix or not. If it's a positive matrix with positive definites, that's what we have to calculate it. If it's positive definite matrix, then it has a minima, and if it's not positive definite matrix, so if it has positive definite matrix, that means it has a minima or maxima. Based upon that, it will be decided. Okay, so we will see one of the example that will clear your doubts. So find the first and second order derivative condition for a function and tell whether minima exist or not. So this is a function which having the two variables. I calculated the double derivative. So double derivative, I calculated the gradient. So gradient looks like this. This is the vector of partial derivative. So derivative with respect to x1. I calculated derivative with respect to f1 x1, derivative with respect to x2, and make it is equals to 0. So now you will have two equations here. This is the first equation is equals to 0, and this is second equation. So when I solve this both system of linear equations, I will get x1 and x2 is equals to these values. I got these values, okay, x1 and x2. Now checking the second order. So for this x1 and x2 value, I am getting my stationary points at this particular values. Checking the second order necessary condition, I will check whether this is positive definite or not. So positive definite is that matrix whose eigenvalues are positive. Okay, is that clear? Do we check determinant? We check, no, you can check determinant. If determinant is 0, then means you will have kind of one of the value is eigenvalue is 0. Okay, but we want both values to be positive definite. Means positive definite is the matrix where you want your eigenvalues to be positive. Okay, so just calculate the eigenvalues here, focus on eigenvalues rather than calculating the determinant, because that determinant will give you a partial information. So within that time you can calculate the eigenvalues. Okay, so positive definite matrix is the matrix whose eigenvalues are positive. Okay, so in this case, once you got this matrix, just try to calculate eigenvalues for that. So here I am calculating the eigenvalues for this particular matrix. So it gives me both eigenvalues to be the positive, hence the matrix is positive and minima exist at a critical point. So whatever that we calculated for this, the minima exist. Okay, so this is the necessity condition. Now we will go to some numericals and you are able to see. Uh, uh, okay, so this is the first MCQ. In multivariate optimization, what is the critical point of the function? So just read the statements and then you can answer. Multivariate optimization, what is the critical point of the function? Okay. So the correct answer is a point where gradient is 0. Okay, uh, gradient or you yeah. So it's a gradient where all the gradient means whatever the gradient matrix we will calculate, it is equals to a 0 matrix, and that's what exactly what we saw. So next question is a multivariate optimization. What is the role of Hessian matrix? Just now we saw what is the role of Hessian matrix. Okay, so the correct for answer is it provides information about the function's curvature. Okay, so it's like uh, means whether your function is kind of at what exactly it providing curvature means kind of you are at a minima or the maxima. So that's why this is the correct answer. So how your function is going, so it providing you the information about your function. If you are in the multiple dimension, so you cannot visualize how your function looks like. So the mathematics or the double derivative form is the better way to visualize the things. Okay, moving towards again mathematical questions. Calculate the gradient of, so just calculate this is your function at point. So I gave you a point, so for this particular point calculate your gradients. So I think means whatever the questions I'm taking, I think all questions will be there in the week assignment. So by solving this, I think you easily can solve those also. Calculate the gradient for this particular point. Take your time. 4x square means 2 multiplied by 4x is the derivative minus. Calculate first derivative with respect to x, then with respect to y calculate, and then solve the system of equations at point 0, 1. I think no need to um, make it is equals to 0 as well. I just asked about the gradients. Okay. Okay, so we will go to the answers. It's minus 3 and 12. So why it's minus 3 and 12? Let's look into the step 1, calculate derivative with respect to x. So I calculated derivative with respect to x. If you do the derivative, you will get x3 8x minus 3y. So y square, so x is not dependent on and y. So this whole becomes 0. Similarly, dou f upon dou y. This is another derivative. So what I asked you at 0 and 1, what exactly my derivative. So this is one derivative and this is the second derivative. Those are the gradients. So I put x and y is equals to those, and you will get dou f upon is equal to minus 3 and 12 is particular answer by putting in those questions. Those who are not able to solve, just take a snapshot and you can understand it more better. Okay, so this is another question. Calculate the Hessian matrix for. So this is a particular function at 0 and 1. You have to calculate the Hessian matrix. So I think this is function given over here itself. So just you have to do the double derivative calculation of this, and you have to produce a Hessian matrix and at 0 and 1. So Hessian matrix is a double derivative form of kind of a gradient version. Okay, Jagannath Rao already calculated as A. Okay, Jagananda Rao. Okay. Take your time. So these are the first derivative I already given to you, which I already calculated. Your job is to just calculate a double derivative, arrange it proper way, and then just put the 0 and 1 value into it. Okay, so we will move towards another. I think Sahitya answer, Meghna answer B. So uh, both of you are correct. I think Jagananda also answer. So the steps I followed here. The so calculate double derivative with respect to x. So I calculated this dou. So this is a Hessian matrix form. Okay. So here you can see these two. Here your job becomes more easier because whenever you are seeing this particular kind of matrix, so these kind of elements, non-diagonal elements, always are same. So I just have to calculate these three values, dou f upon dou x square, it becomes 8, and this all becomes 8. So when I calculate all these values, so 8 minus 3 and 12. So right now add 0 and 1 I add, but you already got the answer, so no need to put all those value here, and that's why your answer is B. Okay, so this is very simple question again. Moving towards next question, a function has a critical point at 2 minus 1. What is the value of function at the critical value? Critical point. So critical points are already given to you. What is the value of function at which critical? What is the value of function at the critical point? I asked the function value and I gave already your critical points. So very simple answer. I think just substitution answer. No need to calculate derivative and all those. Suchita and Jagannanda give answer B A. Okay. Let's wait for the others. Read it properly. I A Saite. Yeah, Suchita, you got the answer B, but that's not a correct answer. So let's just assume means just plug and play. Okay, so I plug because here I asked a function value. I gave critical value. So just put the critical values x is equals to 2 and y is equal to minus 1 in this particular equation, and I ask this value to you. And when I put that, it becomes 8, and the A is the correct answer. Again, a quadratic function is given to you. What can we say about its critical value? So this is the function, and what you can say about the critical value for this function. So here this is a quadratic function with two variables. It's a minima, maxima, what you can say. Local, global, saddle, okay. Okay. So many of you answered as a A. Okay, sorry. Yeah. So it's a minimum. Okay, many of you answered as a maximum. Okay. but it's a minimum. So let's deep dive in this. I think I should provide you the more time. Calculate the derivative with respect to x and y. That's what I calculated and prepared the Hessian matrix. So I then solve the here a Hessian matrix, and I got 5 plus under root of 5. So I got both positive value, and that's why I already told you, if it's a Hessian matrix and if it's a positive definite Hessian matrix, then you will get a local minimum. Okay, and that's why our answer is B, because lambda value, even if you calculate this plus 5 plus root 5, then it becomes some 5.5, and if you root minus 5, then it becomes some 5, means 4 point something like that. So both lambda values are positive, and that's why our Hessian matrix is positive definite matrix, and that's why it's a local minimum. So if such question asks, you have to calculate the Hessian matrix, because here we have the two variables associated with that. Okay, so this is another question. So choose the correct option for a given. Okay, so I provided 1 to 3, and these are kind of you can say local minimum associated statement with that. So these are the statement A, B, C, D, and I am asking you which one is the correct. So okay, so this is the first question, and this is the second question. Okay, so don't confuse. So we are just right now I'm asking about this question. These are the numbers, and these are the figures for that number, and based upon number you can choose whether it's a local minima, local maxima. I think it's a very easy question. Jaganandan Rao C. Okay. Prakash C. Okay. Okay. I answer as A from C. Okay, most of you answer it as C. You all are correct. So, what exactly, why it's a C answer? Because uh, here you are easily able to see maximum here. Here you are able to see minimum. What exactly this? So, this is such kind of a point is called to the saddle point. Why the name is given? So this is looks like when you see the horse, and top of the horse there is a kind of this shape you already saw, that is called to the saddle for the horse. So from that this particular shape, and that's why they call it as a saddle point. From that concept, from that particular shape, this particular shape is also both are similar. So from that it is inspired, and that's why it is called the saddle point. So why exactly this is called to be saddle point? So you can see if you go right hand side, your value is increasing from the function, and if you go this particular again, if you go rotate in 90 degree, you are going again this, and your function is going to be decreased. Okay, f of x function. So the point in which your function will decide whether value of function will increase or decrease, that particular point also called the saddle point. In this case, wherever I will go, I am going to lose my value. Okay. In this case, wherever I will go, I am going to increase my value. But in this case, direction will decide whether my lose or decrease or increase value. Again, this is second question, which is the correct situation. I think you got the answer, and yes, similar question. This is based upon your derivative values. So for the second question, what is the answer? These are the conditions. Saddle point means your derivatives are zeros. Okay, CB. Someone answered as A, B, so it's a mix of answer, and the answer is correct answer is C. I gave here. So first we will see one here. Your double derivative becomes 0. Okay, for the saddle point. So then that means C and D are correct, and then this is kind of a your maxima in which maxima means minimum value. So minimum than 0. So here minimum is 2. This is the kind of a minimum value, negative value. So correct answer is C. Okay. Now we already saw this all condition and all. So, but in the reality, you will not exactly end up with what you can say exact solution. There are the function, but for those function, you will not get the exact value or it's very hard to find the exact solution. We saw all those examples right now. These are all examples. So you can calculate a derivative for this example, and double derivative, and it has a specific exact answer, correct answer for it. But in reality, it becomes very difficult. Okay, so in that case, we use the algorithms and all. So for that case, there is a gradient descent algorithm we generally utilize. So unconstrained optimization problem direct. So here we are. I'm showing you one of the example of the illustration. Based upon that, how it is calculated, we will decide. So let's assume you here on the top of the hill, okay, and you want to reach the minimum, means where you want to reach the lowest sea level from your this particular point, okay. So what decisions particular you can take. So this is the kind of a glimpses I showed to you of exactly you are standing at the, and this is how in reality that geographic spatial version of it, kind of a heat map of it you can see. This is your global minimum, but you are not able to see from this point. This is global minimum, and these are local minimums. Okay, so you are standing at this particular point, right? Now you want to reach particular frame. So for our aim is to reach the bottom point of this region. So if you are standing here, you don't know this particular whole geographic space. First aim is to direction of the descent. Means you have to find in which I am going to decrease my objective function. So your objective function decrease in which area, you have to find your direction. So you will find a direction. Then the steepest direction in which your value is decreasing very fast, that you have to find. And sometimes we climb up, okay. And here let's consider if you are finding this value and you are end up with this. So to get a more better answer, so better answer is reached here. So to want a more better answer, you will go again, you will climb bit, and you will again find another direction, and you will end up with this global minimum point. So it's just with the example what from your intuition you are sitting at the top, you will find, you will look in your surrounding where is there is a downside, and you will go in that downside, you will stop there, and you will look again in that space where I can go again, where I can find. So it's like go see where you can go down, move till that particular timestamp or particular step, again go, again search which direction is fruitful for me to reach my objective, go specific distance to that objective. So it's a kind of a exploration problem, okay. And this can be, you can relate it with the optimization problem. So this is a real life example of optimization problem. To solve this, we generally go with gradient descent algorithm application to find a minima of the given function, which will help you. So whenever someone will ask you minima or maxima, if you just take a function and if you just add a negative sign to it, that becomes a negative, what you can say, maximization problem or the minimization problem. Okay, so it's that simple. Okay, so here we are going to see the mathematical version of it applied in the back propagation algorithm to find the parameter. So if you want to find the minima, so this is kind of a mathematical function it will looks like. So x tells your current position where I am standing. F will give you the distance in which I want to go, and alpha will tell you how much distance that I want to travel in that position, and x k plus 1 will tell you where I will be after solving this particular problem. So x is your initial condition, xk plus 1 is your new condition, okay. This is in the mathematical form, okay. Step 1, iteration start at, if you know the function, iteration start at x, okay, and that is your initial point. Then based upon that you will calculate this particular function, this s search direction that tells you in which direction I want to go. So this particular s is generally a steepest descent direction, and steepest descent direction is nothing but if you calculate the negative of the gradient, and if you take the negative of your gradient value, that exactly tells the steepest descent direction, okay. And what we will do, we will just put that steepest descent here, alpha ks, we will calculate the value of x, and based upon that you will get your next value. So based upon this is kind of a value. So here I'm starting with different initial value, and if you based upon different initial value, I'm calculating this new point. So these points will come, and you are able to see this particular balls reaching at different position by choosing it at a different initial values. Okay, so this is formula is followed here, and you are able to see epoch means how many times I calculated after reaching. So here all these kind of a beautiful animations or GIF you are able to see, because these answers are calculated some 300, 400, around 7 to 8,000 times, and you are reaching at this particular for that particular point. Okay, moving towards next. So here I am want to show with the help of mathematics how the glimpses of this looks like. So let's understand this with the help of quadratic function. So this is my quadratic function looks like. So I'm just want to give the glimpses of quadratic function. So this is my quadratic function. I give the learning rate means how much I want to move. So I want to just move by 0.1. I want to move by 0.1 step only at each step. Initial point I am taking 9 here. Step 1, calculate the gradient of f of x. I calculate the gradient, calculate the next optional point. So this is, I already told you, this is my step. So I'm going to step 0.1. This is my gradient and this is my negative value. That will give you of the direction. So f of x, so if we will put 2x minus 4, and this becomes a full equation. So initial value is 9. So I put all those values 0.1. I put this derivative value, this is 0.1 coming from here, this is derivative coming from it. So it gives me 7.6 is my new value. Then I will put again 7.6 value, then I calculate. So this is how it will looks like. It will start from this here 9, then I again move 0.1. At every 0.1 I am calculating this. So I moved by 0.9, I get this value, moved 0.9. So you are able to see, still I go here, I am getting my values kind of whenever I am reaching to this my solution, my alpha means what you can say, I'm moving towards this, and you will end at this particular point where your whatever your answer getting, that will not change much, and that you can consider as your, if your particular answer means your value is not changing by certain value 10 raised to power minus 3, then you can say that to stop your algorithm. If this is alpha learning rate is equal to 1, if your learning rate is equal to 0, then it looks like this. It will move here, it will move here, here. So if alpha value chose very wrongly, then it might, what you can say, uh, it will be kind of a zigzag pattern, and you will not end up with this particular value. So choose very small alpha value so that you can reach your solution. It will take a more approach, but you are kind of that kind of a guarantees to reach a minimum values. Okay, so this is how gradient descent algorithm looks like. So gradient descent algorithm with different alpha values is as follows. So with this alpha is equal to 0.1, so you can see very smoothly you are going to minimum value. If I increase 0.3, so it takes 24 iteration to reach this value. I'm just giving you the example. If I take this 0.1 value, how many iteration takes? It takes 24 iteration. It takes 8 iteration. Only after 8 times calculation, I reach this value. Here it takes 15 values to reach this. Here it takes 13 values. So based upon your alpha values, it takes in the time, or you can say iteration, to reach that minimum value. But best thing is to go with a learning rate which is the minimum rate, because this, if you took more higher value, it does not, you don't know if this is a function you reached at this particular value. Otherwise it might kind of bouncing back in between this, and you will never reach that particular value. So this is the example again with the glimpses of gradient descent. In algorithms, we generally optimize our error and convert that error into the optimization problem, and we want a particular value. In case of a regression problem, we generally want the your y is equal to mx plus c. So here just they are taking here, if your intercept is at 0, then means c value y is equal to mx plus c. So c is equal to 0. So here our aim is to find the minimum slope of your particular value. So here you are able to see the glimpses of it. So you are finding the error, you are optimizing the error. So your optimization function is error, and you are putting the minimum, what you can say, slope value in this particular places, that is a decision variable, and you are getting this kind of a. So here you can see cost at step 1.1. So if you are here, you are getting this kind of a slope. So here we are calculating the slope and you are getting the best slope at this minimum value. So this is how in background your algorithms works, and based upon that they will reach to the minimum value of this error function, and when you reach to the minimum value of this error function, that way you are this particular slope you are getting, and that's how you are optimizing, or the regression line you are getting. So this is what happens in your backend problems. Okay, so moving towards again examples, find the value of a minimum. Okay, find the value of minima after three iteration of function f of x. So this is your function with constant step size. So I gave your alpha value to you, and initial value I also gave to you. So this is f of x function. We want to find till three steps. So I just give how it is calculating. So this is how exactly in algorithms things works. Okay, but we don't know because these are very fast calculation. So these are our I calculated because there are two values x1 and x2. So I calculated the gradient here. After calculating gradient, what I am doing, I'm putting values. 0, 0 is my values. So this is my x0 where I'm putting 0, 0. Okay, and I already calculated this derivative, so I put derivatives, and I know the initial condition as 0, 0. I will put those initial conditions 0, 0, and I get minus 1 and 0. That is my first step. I put here again minus 0, 1, and put again in the derivative all this minus 0 and 1, and I got the answer for this for my second step. Similarly, I put in the third step and I got for the fourth step. So this is how you have to calculate for the different step. Okay, now we will move towards the exercises. What is the primary goal of gradient descent algorithm? So that's what is the questions. So you will go through it. Hope will the recording of this lecture will be available? Yeah, it will be available. Yeah. Uh, Even if my things not clear to you, I think looking at PPT and I think animations from the PPT that will clear the doubts. I think so. Okay, what is the primary goal of the gradient descent algorithm? To find the global minimum of the function. That what exactly what you. Even if you not reach the global minimum, you might reach the generally it if there are multiple minimums, then you might end up with the local minimum. First important thing is gradient descent not guaranteed to reach the global minimum. If you have multiple minimums, so it might stuck in the local minimum as well. So be aware of those treatments. Next question, in the gradient descent algorithm, what is the gradient? Okay, so many of you understood. So gradient, if you calculate the gradient, that will give you the direction in which I have to move my particular algorithm and all. So you all are correct, right? Next question, what happen if the learning rate in gradient descent is too small? I just gave you the different glimpses of those photos. I think that will clear. If it is a very small, what will happen? B, algorithm converge slowly. Okay, algorithm converge quickly, algorithm oscillate around, or algorithm diverges. Yeah, I think most of your answer from that image, it will converge very slowly. Means it guarantees you to reach a minimum, but it will take a very long time. Okay, so choose your alpha. There is no hard and fast rule to choose the alpha. You can choose whatever you want. What is the relationship between the learning rate and the risk of overshooting the minimum? What is the relationship between learning rate and the risk of overshooting minimum? Okay, Prakash A, Ravi Shankar A. Okay, both of you are correct. Yeah, I already told you if your learning rate is high, you might struggle that it is not reaching the minima and it overshoot your minima. That things already we saw. It is overshooting minima. Okay. Moving towards next question, what is the disadvantages of using stochastic gradient descent algorithm? We discussed, I think, two or three times I stated that. Whether it is very slow algorithm, it can get stuck in the local minima, it introduces high computational complexity. Here, there might be all answers, options are correct, but you have to choose the most probable answer. What is the disadvantages of this algorithm? Most probable. Okay, so most probable, okay, it disadvantage of it can get stuck in local minima. Okay, that's what exactly means. Even if it's slowly, right now the computation powers are very means. Right now you are able to do the real time all things. So it does not means even if your algorithm is slow, right now computation power is so high, so it will not affect that much. But if it's stuck at local minima, then that's a very huge problem for us. So those who provided answer A, you all are correct. I'm not disagree with you, but most probable answer for this, it can stuck in local minimum. What I exactly, you can say, scared about, rather than scaring about it's a very slow algorithm. In your When you're training model, generally they use generally the different versions of stochastic gradient based algorithm. Okay. uh, there is a one concept called parameter and hyperparameter you will come across. So parameter means in when you talk about y is equal to mx plus c. So those slope and intercept all called the parameter, but here alpha value as well. Here we choose the alpha value, right? Alpha means how much steps I want to choose. That is called to be the hyperparameter. There is a no hard and fixed rule to choose the hyperparameters. Simply in the neural network, how many number of nodes I want to choose in the random forest, how many trees I want to choose. There are no hard and fast rule to choose all those things. That's why it is called to be the hyperparameter. So that's very basic difference between the parameter and hyperparameter. Okay. So moving towards next, in the context of gradient descent, what is the formula for updating the parameters? So this is formula already we discussed. Okay, so what is the A is your alpha means shape and G is your gradient. So what is the answer for this formula? G is your gradient. We just saw the formula. B A, okay. So the correct answer for this, uh, so um, the correct answer for this you can consider A option. Okay, it depends how you means. I think you can for now just take A and B are all both are correct. The correct formula is B. Sorry, the correct formula is kind of it depends upon the gradient. If you calculate the gradient and take the negative value of it, then it becomes this particular B answer. And if you just taking the negative value and just calculating the gradient value here, then A is the correct answer. Just try to take a negative gradient. That's most important. You should have in mind. Okay. Moving towards next, if the gradient of function is and the learning rate is, what is the updated gradient descent step? I just asked the second step. So calculate the gradient and make minus and then take the gradient. Calculate the gradient, make it negative and then put into the formula. So I already gave you gradient, means I already gave the g values. Okay, I think I not got it. What the updated gradient step? I asked about updated gradient step. How much you want to move from one step to another. I'm just asking about the distance. I'm not asking about the next values. So answer A, answer C coming for me. Okay, let's figure it out. Why? The updated step calculator for subtracting your time. So um, gradient from the current values. So minus 2 multiplied by 0.1 and 3 multiplied by 0.1. Okay, so it becomes minus 2, 0.2 and 0.3. By this only I want to go. So again, it's just how we think. So it's either A or you can say either C option, both are correct. Because you guys consider it as a negative value put, then also it's a correct. Okay. Moving towards next question, if the initial parameter value is 8 and the gradient descent step is 0.2, what is the updated parameter value after one iteration? So I'm asking updated parameter value after one iteration. Initial value is given, all gradient descent value is given. So moving towards the answer, it's a 7.8. The updated parameter value is calculated by subtracting the gradient descent step and the initial value. So here just I twisted a bit question. Gradient descent step is already given to you, that is 0.2. Means I already calculated gradient multiplied by alpha value, so that is 0.2, and initial parameter is given, so correct answer is 7.8. So it's just a twist of the word way I am saying, or it's written here. It's not that complex. Okay. So that's it for today. So if you guys not understood anything, you can just ask me, or put in the chat box, or you can just, I think mics are on, you can ask in the mics as well, because there are so many less people, so no disturbance today. You can ask me the questions as well. So I'm concluding that this is the end of the session. If you're not able to understand or not understood something, just put in the chat box, or you can directly ask by opening your mic. Hope I covered all the questions. Uh, if you not understood any concept, or not understood any question, um, please ask. So another question means I have means, are these sessions helpful for solving the problems or not? Can you give your feedback? Means genuine feedback. If it's no or yes, uh, if you're not understanding or partially understanding, so that I can improvise on the part, or I can take more questions like that. If you are not, means you can put in the chat box as well. Not an issue. Okay, so far I think no. Okay, if you are getting it, then put, yeah, we are understanding it. If you don't want to give the feedback and all, yes, no, you can say that. You guys are understanding it or not? Okay, okay. I assume your silence as you understand all the things. That's it from my side today. Uh, Thanks to all. You can leave the session. I think it's Sunday, so you want to leave, so that's why I took the smaller session. We will meet in the next week on the same time, Friday schedule. Thank you. You are free to leave the call. Thanks a lot.